This is problem 55. A car traveling at 16 meters per second sees a truck 20 meters ahead, traveling at a constant speed of 12 meters per second. After thinking it over for 0.8 seconds, the car starts to accelerate at 4 meters per second squared in an attempt to rear-end the truck. The truck driver has paid up insurance, so doesn't care. The car driver's motive is unknown. Since the truck driver doesn't care, the acceleration is 0 for the truck during the whole time. Event 1 is when the driver of the car sees the truck. Event 2 is when he's finished thinking about whether or not he's going to rear end the truck. So at event 2 he starts to accelerate, and event 3 is when the car rear ends the truck. So initially the acceleration of the car is 0, so the velocity vectors have the same length until we get to event 2, and then the car starts to speed up for the truck. The truck starts ahead of the car, so the truck starts here, and the velocity vectors are the same length the whole time. We draw a velocity versus time graph for the truck. The acceleration is 0, so this is just a flat line for velocity. And for the car, it's flat when the driver is thinking over, and then the driver accelerates, speeds up, so the slope is positive. Okay, so I have all the information that was given in the table here, and then I look between event 1 and event 2 for the car. I know the time is 0.8 seconds, the velocity is 16, so I just multiply the base times the height, 0.8 times 16 to get 12.8 meters, and that is R2 for the car. Then for the truck, similarly, I'm looking for the area underneath the curve and up until we get to T2. The area is delta R12, that's R2 minus 20 meters. And so the area is 12, the height times T2 is 0.8. That gives me 9.6. So the area underneath the curve is 9.6 meters, but that's R12 for the truck. So R2 is 9.6 plus 20. That is 29.6 meters. Then I go from event 2 to event 3. There is nothing interesting to do with the slope since it was flat for both the car and the truck between event 1 and event 2. So for the truck, when I go from event 2 to event 3, R3 minus R2 is R3 minus 29.6. Since the acceleration is still 0, the area underneath the curve is delta T23 times 12. And R2 is equal to 29.6. I can bring that over to the other side. It was minus R2, so now it's plus 29.6 on the other side. Delta T23 is T3 minus 0.8. That was times 12. So now I have an equation for R3. R3 is the same for the car and the truck, so I can just call it R3. R2 for the car and the truck was different, but if I do my work for the truck over here and I do my work for the car over here, I can keep that straight, even if I didn't call it R2 truck and R2 car. Okay, now over here, looking at the car, the slope is 4 for the acceleration. That's V3 car minus 16 over the time, which is T3 minus 0.8. So I have one equation, a second equation here. I need one more equation, which comes from looking at the area. And the area underneath the curve as you go from 0.8 to T3 is R3 minus R2, which is 12.8. I can use the average height here, so this extra piece fits in down here. The average height is V3 car plus 16 divided by T2, and the base from here to here, that's T3 minus 0.8. Now I have 1, 2, 3 unknowns in this equation. 2 of those unknowns are in this equation, and R3 is the same for the car and the truck, so 2 unknowns in this equation also. I can solve this equation for V3 car, put it in here. Now I have 2 equations, 2 unknowns, can bring the 12.8 over to the other side. Now both these equations are R3 equals something, so I can set those equal to each other, solve for T3 using the quadratic formula, and I get 2.9 seconds, so I can put that in. So that is T3 because we put the minus 0.8 in here. So that goes right up here. That's 2.9 seconds. If you kept this as delta T delta t to 3 instead, then don't forget to add 0.8 to delta t to 3 in order to get t3. So this is 2.9 seconds. Then you go back to your 3 equations here to finish filling out the table. R3 is 55 meters, and V3 for the car is 24 meters per second. And that's problem 55.